Good morning. Today I'm going to talk to you guys about the laws of thermodynamics, and I've simplified them a bit based on what we need for the class. Obviously, there's a lot that's going on with the laws of thermodynamics, so you could spend really years studying this stuff. But we're just going to hit the highlights, if you will. And the highlights as they particularly describe actual machines. And so that's what I'm going to try to do for this. So hopefully I'll try to breeze through it pretty quickly here. One thing you need to know is that there are actually 4 laws of thermodynamics. The first, the second, and the third were developed first, which I know sounds strange, and then later on people decided that there needed to be a law before the first, just as a foundation for the first. And so they didn't want to reorder all the numbers because everybody had memorized them and learned them that way, and so as a result they didn't want that confusion. They decided to name the first law actually the 0th law. So the most basic of all the laws is the 0th law of thermodynamics, which I know is weird, but it is what it is. It's kind of like when you have a piece of software and the version number is like 0.5. That's kind of what they have here, but it's not. I mean, it's not quite the same. Anyway, you get the idea. So the 0th law says if heat does not flow naturally from one object to another, they must have the same temperature. I should put in there that naturally, and so it's important that you understand we're not talking about forcing heat to flow. I mean spontaneously, without any additional energy being added to the system. It will flow naturally from one object to another if they have different temperatures. But once they have the same temperature, heat does not flow anymore because they've reached thermal equilibrium. Why is this important? Because it's the basis for us using thermometers. So here I have an old style alcohol thermometer with the red alcohol solution in the center there, and we've placed it into a water bath. So, what will happen in that water bath here is that heat will either go into the thermometer from the water, or it will go out of the thermometer into the water. Now the thermometer is really small, and there's a lot of water in this case, and so as a result, if heat does leave the thermometer, it doesn't really affect the water very much. But if heat leaves the water and goes into the thermometer, that affects it quite a bit, because the thermometer is small and it's made to be very responsive to changes in heat. And so as a result, we see heat flowing from one to the other. And that heat flows until they are the same temperature. So no matter which way it goes, if it goes from the thermometer to the water or from the water to the thermometer, it's going to equalize until finally they have the same temperature. That's not to say they have the same amount of energy. That's not it at all. What it is that they have the same temperature. So hopefully that makes sense. And that's temperature is kind of the key for all of this. You have to remember that the temperature of an object is really just a measurement of the amount of shaking of the particles, right? The vibration or motion of the particles that are in that particular object or substance. And so that's really what we're trying to establish here is the basis for this idea of temperature, which is kind of weird. If you think about it, it's kind of cool that this works the same for all substances. So you don't need one thermometer for alcohol and another thermometer for water and another thermometer for hydrochloric acid. You can use the same thermometer on all 3 and it will work just fine. And it's because of the fact that heat is the same for all objects and temperature is the same idea for all objects. Quick to the first law. First law says the amount of heat an amount of heat may be used to do an amount of work, but the work that you get out is always less than the heat that you put in. So heat is a kind of energy. Okay, so you have to remember that heat, when we talk about it, is really another way of saying it's another flavor of energy. And so you may remember from earlier on, we talked very extensively about the fact that however much energy you have in the system, you're never going to get that much work out of it because of the fact that there's things like friction and other resistive forces. So here I have kind of a simple version of this. So in this side we have hot water vapor or steam, and so you can imagine that you have somehow heated up this water vapor so that it's extremely hot. And then you connect up this bulb, this part of it, to a cooler area, right, where there's cool, so low heat or low temperature. And so as a result, what you can do is you provide a path for the steam to get to this area of low temperature. Now, one of the things that steam does is it expands. And so as it gets warmer and warmer and warmer, those particles shake around more, and they end up expanding out into as much area as they can take up, as much volume as they can take up. And so as the particles expand, some of them push their way this way through the opening in the bulb. Now, being smart, people in the 19th century said, hey, if the steam is going to naturally flow from one area to another, to an area with high heat or energy to an area of low heat or energy, can't we put something in between to try to get some of that work out? And so we can put a turbine. And so we put a little fan blade right here. And as the steam is trying to push its way towards the emptier, lower pressure area over here, that steam has to push its way through that turbine. And so as a result, the turbine is made to spin. Now, if you remember anything about work, work is force multiplied over the distance that it's being applied. And so what this is actually doing is it's pushing those fan blades around in a circle. And so it's doing work on the fan blade. And so as a result, we can get the steam to do work for us as it moves its way from one side to the other. Now there's a couple of problems with this. One is that we can't take all of the friction out of this fan blade, and so some of the energy, you can think about energy as flowing from one side to the other. Some of the energy goes out, right, in the form of useless energy. We would normally call thermal energy, but to make it different from the energy that we're talking about in the system, we're going to call it useless. It can't be used to do work. And so that friction forces some of the energy out of the system. And so the total energy that's available goes down. But some of the energy can be used to do work. And that work is right here shown by moving a fan blade. There's lots of other ways to do work from heat, but that's kind of the easiest way to envision, I think. That's the first law. Now the first law is actually also the law of conservation of energy. So what this says is you cannot, under any circumstances, create or destroy energy. And so if you can take into account all of the work done by a system and all of the energy that's in the system and all of the energy that becomes useless and leaves the system, you'll find that amount is exactly the same no matter what happens. Hopefully that makes sense. We've talked about the law of conservation of energy a bit in here, so just remember it's been a long time, so just remember that. The second law of thermodynamics is actually the most important of the laws because it has all sorts of crazy philosophical implications. We're not going to talk about any of those, although if you want to, we can. It says, in any system, the total amount of useful energy, or energy that can be used to do work, always decreases. So because of this loss of energy, it doesn't go away, it's not destroyed, it just leaves the system, or leaves the useful part of the energy in the system. Because of that, all of the useful energy in any system is going to go down over time. And so it's kind of a cool idea. This is one of the philosophical implications, so I guess I'll mention it here. If you think about the universe as a system, the universe had all ordered energy, or all useful energy at the beginning in the Big Bang, and then over time it has gotten less and less and less useful. And so as a result, there will be a point, billions and billions of years into the future, where all of the useful energy becomes useless. And that unfortunate theory is called the heat death of the universe. At some point, the only energy that'll be left will be this kind of useless thermal energy. And so there's not much that you can do. Humans will no longer be around at that point because humans have useful energy in them, and so they would not be allowed to exist at that point. But again, we're talking about billions and billions and billions of years from now. Okay, but you can increase the amount of useful energy in a system. So I could, if I wanted to, let's say I used this to get work out of this turbine. And it did that. Everything was great until the temperature on this side and the temperature on that side equalized, as we talked about in the zeroth law. So the energy naturally flowed from this side to that side until the temperatures were the same. So how could I get this system to work again? Easy. I could add in heat. Right here, I could heat this back up. And if I wanted to, adding in that heat then would make this back into steam again, and that steam would want to naturally flow to the other side. Now, for this to work perfectly, you'd have to probably take some things into account, like you'd have to cool off the steam into liquid water, and then you'd have to pipe the liquid water back over here. And there's all sorts of logistical considerations that you'd need to take into account. But this is really how coal plants and nuclear power plants work. They use some source of heat to create steam. That steam is then forced to, or is then allowed to, move through a turbine, which spins, which we use to create electrical energy. And then it goes to a place where there's a low temperature. And then all they have then is the water. The water condenses back into a liquid, and they have a pipe that runs back that way so that it connects back up, so that some of the liquid water can come back here to form steam again later on. And so it actually ends up being a closed loop if you think about it that way. And so people who are worried about nuclear power plants, about the water from nuclear power plants getting out, the water that comes closest to the actual nuclear energy is all in a closed loop, so it doesn't really leave the system. There is other water that's being used to cool off this, and that actually leaves the system. And that's why you'll find that nuclear power plants are always built on lakes or rivers, like the one we have in Two Rivers. Anyway, so that's the second law of thermodynamics. It's a crazy, crazy law, and it has a lot of depth to it. But for us, the important thing is that you can just think about it like this, that you can add energy back into the system to get it to work again. Now, one other little point is that you can actually cause energy to flow from low temperature areas to high temperature areas, like what happens in your refrigerator. You can cool off the air in your refrigerator by doing work on it, but you have to put in more work than you're getting, than the energy flow comes out of it, because of the fact that there's friction in the system. And so you may have heard your compressor in your refrigerator running. What it's doing is it's doing work to be able to force energy to go from inside of the refrigerator, the air that's inside the refrigerator, out into the natural environment. So if you feel the back of a refrigerator, you'll feel that it's hot back there. Why? Because it's taking that heat from inside and pushing it out, but it has to do work to be able to do that. And then last, there's the third law of thermodynamics, which just says, if you're going to try that, if you're going to try to do work on a system to try to move the energy out, you might imagine that there's a point where you can't move any energy out anymore. And it turns out that this is kind of an important point here. If you have a system, and that system is something like this, where you have warm particles that are vibrating back and forth and back and forth, you can do work on this system to be able to cool it down. And if you cool it down, those particles then are slower. They move less and vibrate less and bounce around less. I'm using a gas here just to kind of give you the idea. So you've got motion, all this motion here, like so. And then cooler would be less motion. And the way that you do that is you put in work. So I can do work on the system to cool it off, just like your compressor does in your refrigerator. But could you make a refrigerator that took out all of the motion of the particles? Well, it seems like you could, and that temperature at which you would no longer have any motion of the particles would be 0 kelvins, or what we call absolute zero. But in reality, you can't do it because energy always leaks back in. So there's no way to make a gas or any substance that has no motion of the particles left. What we do now is we take lasers and we shoot lasers at these atoms, like so. So I shoot a laser at this side and that side and that side, and this side and this side, this side, all at the same time. And so this little particle that's on the inside there gets hit by a laser from every single angle all at the same time. And as a result, it gets very, 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 very low motion. And so we can get the temperature down to basically millions or billions of a Kelvin. So really close to absolute zero. But the problem is that you have to keep that system so isolated from the rest of the universe that you have to try to keep as much energy from flowing in. As we found up here in the zeroth law, energy will naturally flow from places where there's a temperature difference. So we've made the coldest place in the universe here. Energy is going to try to flow in from every possible way. And so it turns out that it's really hard to do that. And in fact, given theoretically, even though it's theoretically possible to get to absolute zero, there is absolutely no way. It would take an infinite amount of energy to be able to keep all the energy out. So obviously that doesn't actually happen. So those are the three laws of thermodynamics. Sorry this was a little bit on the long side, but there's a lot here. So you will see probably a couple of end of course exam questions about it. If you have any questions on it during the class, please let me know. We'll talk about it then. Thanks. Bye.